welcome to the lectures on evolution of wireless communication towards 5G. So, what we have discussed till now is the different waveforms which are futuristic, which have been investigated and which require even more attention for them to be made mature towards acceptance in the next generation communication systems. And we have seen a variety of waveforms, namely the filter bank multicarrier, then unified universal filter multi-carrier waveform. We have seen faster than Nyquist. We have also started seeing generalized frequency division multiplexing. So, we will start looking at GFDM and we will complete the discussion on such different waveforms. So, we have said earlier in the previous class that GFDM is the generalized frequency division multiplexing, and hence it is because of the generalized form, it is flexible in the time and frequency resources, which we have been seeing. We will again see it today. It is also resilient to synchronization compared to OFDM, because in OFDM we have seen that because they are a sync in nature in the frequency domain. So, although the others are orthogonal, that means the peak occurs at the 0 of the neighboring subcarriers, but a slight offset causes a huge penalty because of intercarrier interference. And we have also seen that because there is a guard interval or a cyclic prefix. So, if the guard interval is small, then and the channel impulse response extends beyond the CP, then there is ISI and ICI, which causes further degradation in the performance. So, GFDM has a better resilience, and it has good spectral efficiency because it uses circular pulse shape, which we have seen in the previous lecture. The problems are it has high complexity, out of band leakage is still present, but there are mechanisms to reduce it. PAPR is high, but again there are mechanisms which have been proposed to reduce the PAPR as well as out of band leakage. So, as well as reduction of complexity. So, with these additional features which have been introduced into this GFDM, it is now in better shape and is a good contender for the next generation waveforms. So, as you are seeing that we are looking at waveforms, trying to build waveforms with certain good characteristics, but once you try to build one good characteristics, the other one falls down. So, the engineering part of it is to improve overall characteristics of the waveform and provide it with better features than what existed in the previous generation systems. So, the GFDM, as we had seen in the previous lecture, is that we compared with OFDM. That means, with OFDM we had separate subcarriers. So, these were different subcarriers that were present, right, and the subcarriers existed for a time duration, right, and each of the subcarriers were having different carrier frequencies, right, and so on, right. That is how these were present. In the single carrier FDE, we have also discussed single carrier FDE. Since it is a single carrier, it covers the entire band and it is kind of small duration of symbols because the bandwidth is large. So, in one case it is FDM, that is what we had written. In this case it is more of a TDM architecture. In GFDM you have both FDM combined with TDM, because it is a block based OFDM, it is a block based system. So, there are m blocks in time domain and there are n subcarriers in the frequency domain. So, that is how the whole system is, and we have compared with OFDM, like this is one OFDM symbol duration, this is second OFDM symbol duration, this is the third OFDM symbol duration. So, here you have blocks of GFDM and there is one cyclic prefix in front of it, thereby helping it to have a better spectral efficiency even than OFDM. The subcarriers overlap and hence there is no loss of spectral efficiency. So, these are some things we have seen, and this picture also we had explained in the previous lecture, where we said that one can think of the pulse shape. So, if we think of this pulse shape, which is spanning over longer duration of time. So, once you have a long duration pulse shape, then you naturally can make the spectral occupancy of that particular symbol to be pretty sharp. That means, it is not spreading across in the neighboring sub bands. But now, in GFDM what we have seen is it has circular pulse shape. So, what does that mean is that this pulse shape is if you look at the whole thing, there is one time block, second time block, third time block and the fourth time block, Alright, these are the 4 time blocks. So, there are m is equal to 4 in this system, in this particular diagram, and in one time sample, in one time block, the pulse shape would be this. So, it is basically the pulse shape is expanding beyond one time block or one symbol duration, and that one can compare with the partial response signaling, whereas in OFDM it finishes within one time block n samples. So, as you shift the symbol pulse shape to the left and the right, what effectively happens, I mean this is a more simplified diagram, but if you take a extreme shift, that means for the first symbol. So, if it is the first sample, here instead of shifting it just linearly, you do a wrap around or you do a circular shift. If you do a circular shift, then what happens is, as you get over here, pulse shape which looks like this for the first symbol. For the second symbol, it is this one. For the third time block, it is this one, and the fourth time block, it is this one. So, that means if we try to draw it afresh, okay. So, what we have is in the first time block, the pulse shape is something like this, and all the subcarriers are carrying the same pulse shape. Okay. Subcarrier 1 to subcarrier n. Okay. In the next symbol duration, the pulse shape, I should choose a different color, would be for the first subcarrier, it would be something like this. For the last subcarrier, it would be like this. Okay. For the next time block, we can change the color to maybe black. We will have the pulse shape which is going like this, and for the nth, the pulse shape would go like this, right. And then for the last one, we can again change the color to give an indication. For the first subcarrier, it would look like this. For the last subcarrier, it would look like this, right. So, this is how they will be, and you can complete the notation. This is the first subcarrier, this is the second subcarrier, the third subcarrier, and so on, right. And if we choose the different colors to indicate, so again you are going to have on the first subcarrier, and you will also have in the last subcarrier, you will also have this color in the last subcarrier, you will also have the same color, the bluish color in the first subcarrier, and so on, and also for the black, right. So, that is how the whole structure looks like. Now, if one would compare this with OFDM, one could say that if we roughly partition this, okay. So, roughly if we think if in this manner, so then in OFDM case, you are going to have 1 symbol, 2 symbol, 3 symbol, and 4 symbol, and each of them are going to have their own CP, right. So, this is for OFDM, right. So, this is how they would contrast against each other. Time domain, although all the frequency components would be present. So, here all the frequency components would still be present 1 to n. So, that means in each symbol duration you are processing n samples, whereas in case of GFDM, what you are doing is you are taking this whole block together, and then if there are m number of such time blocks and if there are n subcarriers, so you are getting m times n samples to be processed in one go. So, this is one of the major differences between OFDM and GFDM to look at it in a generic way. One can also think of putting different pulse shapes. So, basically this is your GT, okay, and this one if we write this GT is your G of t minus let us say 1t, and then we can have the black one as G of t minus 2t, and then the green one we can have g of t minus 3t, and so on and so forth, right. And all of them are having the same on the same subcarrier. So, if we look at this, this is g t e to the power of j 2 pi k by n, and k is equal to n in this case. Okay. All right, and that is how you are translating. So, the g t is translated in time as well as it is translated in frequency as in the Gabor framework what we have defined earlier. So, this picture might be able to help us to understand the overall picture or overall explanation of a typical GFDM system. Okay. So, now we get back, and this particular picture is also relevant for us in our discussion. So, if we take this particular pulse shape which is for the first set, we will find in frequency. So, these are the corresponding frequency spectrum occupancy of the different carriers, right. So, what we have is that here as you observe, we have the first column, okay, then the nth column. So, first to n minus 1 to n minus 1 column of the GFDM modulation matrix would indicate the n subcarriers. Okay. The nth to 2n minus 1 would indicate the same subcarrier. So, 2n subcarrier is basically the first subcarrier, and sorry, the 2n subcarrier is the first subcarrier, and 2n sorry the nth subcarrier is the same as first subcarrier, and 2n minus 1 is the same as n minus 1 subcarrier, right, like that. So, similarly over here in this set, what you will also find that 2n to 3n minus 1, and here you are going to find 3n to 4n minus 1. So, overall so again what you will find is that 3n is the same as the first subcarrier and 4n minus 1 is the same as the n minus 1th subcarrier. So, like that they are arranged. So, again first subcarrier first symbol, first subcarrier second symbol, first subcarrier third symbol, first subcarrier fourth symbol, like that they are arranged. First subcarrier, second subcarrier first symbol, third subcarrier first symbol, fourth subcarrier first symbol, and like that. So, this is how you have to visualize the entire picture. Okay. So, for these set of columns we have the spectrum occupancy given in this particular picture. So, what you find is again Gn and Gn shifted in frequency by the exponential function, and here what you find is Gn, and then it is shifted in time by these frequencies by these time samples, and by modulo mn it means there is a circular shift. By means of circular shift you reduce the spreading in time, and thereby you have a more compact signal in time, but the flip side of it is the out of band naturally becomes more than if you would have let it to grow in a linear fashion. So, this is the overall framework for GFDM that we are looking at. Okay. So, this is how these entire set of equations that we had described can be visualized in a graphical manner, and this whole equation that we have over here can be represented in a matrix notation, and the A matrix, which is the modulation matrix, is contained of elements where this G is the first column is the GT, you can think of it as the GT, and then all the columns up to the n minus 1 column or the nth column are basically the frequencies translated one. Then the first column over here is the time translated version of this, and the second column over here is the time translated and first frequency translated version of the original Gabor atom. Yeah, that is how one can think of the entire structure and can understand the whole picture. Okay. So, this picture we had explained, and now you can naturally follow through all the descriptions that we had given earlier. Okay. So, if we look at the situation now, so what we see is that x is equal to a d, where d is the vector of constellation points, A is the modulation matrix, and x again is the vector of GFDM modulated symbols. So, here this is m n cross 1, and this again would be m n cross 1, and this would be m n cross Mn, right, this modulation this GFDM modulation matrix. All right. So, that is how the whole thing. So, Mn number of samples are available, and so we have the entire equation now. So, AD represents the X GFDM modulated signal, H represents the channel, which is the convolution channel matrix, right, and H is the channel impulse response, and we can get the received signal in Z, and this is how we can write the entire set of equations. So, if H is the circulant channel matrix, which represents the convolution operation, and so basically you have X times H is equal to Z, and of course, there is noise term which gets added. So, instead of X, we are writing that matrix equation AD. Okay. So, now if we look at Z, we can expand H, because it is a circulant matrix, in this form, okay, where Wmn is a m times m order IDFT matrix, right. This is a natural way of factorization, and these are the eigenvalues, or this, in other words, you can think of it as the Fourier transform of these coefficients. Okay. So, this is the diagonal or the channel frequency matrix, right. So, this is how you can expand the whole thing. So, this is what is the received signal. So, what we are now going towards is how do we recover D from this Z that we have received. Okay. So, for receiving, there are two ways of doing it. One is known as the two stage receiver. In the two stage receiver, the channel is equalized first. Okay. First you equalize for the channel, and then you followed by GFDM demodulation. Okay. We have written GFDM self interference. The reason is, if you look at this AD is such that everything is mixed up. It is not necessarily an orthogonal matrix. It is generally a non-orthogonal matrix, and hence there is a lot of self interference due to operation. At the receiver, if I do A Hermitian A, then it is a matched filter operation, and we are going to get a huge amount of self interference, but at the cost of certain other advantages which GFDM provides. So, when we are equalizing at the receiver, what one needs to do is, if you look at the previous expression, we have W lambda W Hermitian. So, we have W lambda W Hermitian, right, and AD, right, this is your equal to Z. So, now what is being done is this is being multiplied, right. So, if you multiply that, what will you get is W Hermitian W is identity, and then in case of AEQ. So, this is basically the channel equalization part. Okay. So, this is a zero forcing frequency domain equalization. So, in case of zero forcing frequency domain equalization, instead of AEQ, the lambda equalization, EQ indicates equalization, you can take it as lambda inverse. So, the moment you multiply W with W Hermitian with W, you are going to get, so basically you replace this Z with W lambda W Hermitian AD, right. So, this will produce an identity, and then you have a product of lambda AQ with lambda. So, this is your choice of equalization matrix at the receiver, and you can choose it to be lambda inverse. In that case, this product will again produce an identity matrix, then again W Hermitian will again be identity, and then you are left with AD. So, that means if you are using the lambda inverse of AQ, then your received signal can be written in this manner, and then you can recover the whole thing. So, whereas instead of doing zero forcing, you can also do a MMSE equalization. So, in case of MMSE equalization, your MMSE equalizer lambda EQ would look in this manner, and instead of so once you have done this equalization, so you will be left with so once you are done with that, you will be left with lambda AQ, okay, lambda AQ times A and W Hermitian, sorry, lambda AQ lambda, this is not A, lambda AQ lambda A D, and here you have a W. Okay. So, this whole thing now needs to be equalized. So, generally you would have it in a way that this cancels out the interference either by MMSE procedure or by zero forcing equalizer, and then whatever is remaining you would have to equalize that with AEQ as the equalizer coefficient for A, and then you need to recover the whole signal. So, for matched filter operation your AEQ would be equal to A Hermitian, and for zero forcing it will be A inverse. Okay. For MMSE it will be, which looks like this, where this is the covariance matrix of noise, and for unbiased you have to modify this expression with a factor, extra factor, which is described in this particular equation. So, again these works can be these details can be found in some of the references which we will provide in the material, and you can easily go through the derivations and find out how this kind of things work out. So, you have to equalize the channel and then you have to equalize for the GFDM modulation matrix. Now, if you compare this with OFDM, you will remember that A matrix, which is the GFDM modulation matrix, is comparable or it is equivalent to a IDFT matrix at the transmitter for OFDM. So, if you write W with the IDFT matrix, then this will be the IDFT matrix for case of OFDM, and the sizes of course will be different. This is a Mn cross Mn, and this is usually N cross N matrix. So, you can also compare with a Mn block size of OFDM to take Mn samples simultaneously. And when you have to equalize both the channel and the GFDM modulation simultaneously, so what we have is Z is equal to HAD, right, that is what you get. So, Z is equal to HAD, right. So, now you have to recover D. So, HA together you can assign it to be equal to B. So, you can write whatever you have received as BD plus noise, and then you have to find a B equalizer matrix which can cancel or normalize the problems that has been introduced by the B matrix. So, here again the MMSE equalization would be in this manner, and the unbiased MMSE would be again a modification with the scaling factor, which is also described over here, and details of this are available again in the papers that we can provide to you. Okay. All right. So, now these receiver operations, although they appear straightforward in the mathematical notation, but implementation of MMSE is not a very simple job. It is very complicated. You can see a lot of matrix multiplications that happen over here, and there is matrix inversion. So, the order of complexity is very high. Without doing any reduction of complexity, any matrix inversion or multiplication is typically around order of n cube. Although you can bring it down to n to the power of 2.7 or something like that, but it is still very close to order of n cube, let us say. So, you can easily imagine the amount of complexity that is involved, and then there is a set of low complexity transceiver architectures which again we can provide as reference, but we will not discuss in this particular lecture, because those are special aspects only for those who might be interested in the very great details of such receiver architectures. So, we will skip a few set of things, but it will be made available for those who are interested. So, we move forward and look at another modification of GFDM, which is called the pre-coded GFDM, and we will briefly tell you about this. So, in the receiver you basically have A Hermitian A as the operation when you are doing matched filter. So, if you study these characteristics of such matrices, these matrices turn out to be block circulant with circulant blocks. Again, details of these are available in reference papers which we will provide to you. So, that means there are block structures. There are block structures which appear in a circular fashion, and within the blocks also you will find that there is a circular symmetricity that is present in it. So, that is exploited in factorization. So, A Hermitian A can be factorized in this manner, where FBM is the block IDFT matrix, and if you are doing HA, that means channel together with the modulation matrix, then you will be again having another similar factorization, but this is of size n, and in this case this will be of size m. Okay. So, now if we look at the way these signals are, okay, and these can be factorized with block IDFT matrices, right. So, the good part of all of this is whenever we talk of IDFT, we get low complexity implementation. right. So, once we can realize this in terms of IDFT operations, we will get a great advantage in reducing the complexity. So, all that we are seeing over here is that in this processing, if we could somehow use this factorization and split the processing complexity between the transmitter and the receiver, then we can reduce the complexity of operation at the receiver quite a bit. All right. So, in this manner, if you look at the whole factorization matrix, right. So, we should be able to do a lot. So, that means H A Hermitian H A operates. So, if you are at the receiver, you would be able to get this whole factorization, and then you can do some IDFT operation on this side, IDFT operation on the other side, and you would be able to manage the operation. However, from this we have this motivates us to pre-code the GFDM modulator with FBM, right. If you are going to operate on a Hermitian A matrix, and if you are going to operate on this joint processing, that means if you are going to take H A together, then you can do a pre-coding with FB. So, if you are doing pre-coding with FBM, then your FBM on data, you write FBM on data, and then you get this particular part. So, what you see over here is that A Hermitian operation should be done at the receiver. So, if this operation has to be done at the receiver, then the receiver sees A Hermitian A, right. So, if the receiver sees A Hermitian A, so A Hermitian A can be factorized in this form, right, and where D is a matrix which is of this structure, okay, which is of this structure. So, if we can get this D matrix, we can demodulate our signal finally. We have to equalize for this D. To reduce the complexity, you can pre-process at the transmitter with this, and then you only have to process it with the block DFT matrix at the receiver side, right. The same thing applies in case of the HA based operation. So, what we do is we do a pre-processing with either FB, that is block IDFT matrix of size M, or FB of size N, depending upon whether we are going for two-stage processing or we are going for a joint processing, right. So, at the transmitter, you choose one of the options depending upon a pre-agreed condition, and then the signal goes through the channel. When it comes to the receiver, if depending upon the mode of operation, it would either go via this path or it will go via this path, right. So, in the two-stage receiver case, there is a frequency domain channel equalization which happens first, and then at the receiver you are doing a DFT based operation, and then a D blocks equalization happens at the receiver. In the other case, as you can see over here, in the matched filter reception, you are doing a FBHA multiplication at the receiver side, followed by this this D matrix based inversion in order to get the particular detection symbol out. So, what are the benefits of doing this pre-coding is what we are going to briefly discuss, and again all these details are available in this particular paper, which is again easily available. Okay. So, with this we also move to another form of pre-coding, which is called the DFT pre-coding, okay, and this is also available in this particular paper. So, one should feel free to download and get into the details. So, here the idea is relatively simple. Here we do a pre-coding with DFT spreading matrix in a similar fashion that DFT spread OFDM or kind of systems or SCFDMA kind of systems are handled. So, with this DFT pre-coding, then there will be a subcarrier mapping matrix followed by the GFDM operation. So, this is the pre-coding that happens in case of DFT pre-coding, and here these are the possible pre-coding options that happen in case of GFDM. So, here on you are seeing that the GFDM operation is happening. So, here also you are seeing that GFDM operation is happening. So, these things are happening before at the transmitter, and at the receiver accordingly you have to do the reverse processing, and then you get back your data. Similar manner, in a similar manner, because you have H is a matrix, A is a matrix, you would be able to also decompose into a singular value decomposition based structure, and in that case you would be able to pre-process it at the receiver. Like at the transmitter side you could pre-code it with a V, and at the receiver side you would multiply with a U Hermitian, and then you can get back your original data, and this kind of a system you would call a SVD based pre-coded GFDM system. So, here you have a SVD based pre-coded GFDM system, but this depends upon the channel matrix, right. Here also this one there is no dependence on the channel. In this case there is dependence on the channel only when you are doing the channel joint processing. If you are not doing the joint processing, then there is no dependence on the channel over here. In this case there is no dependence on the channel. In SVD there is somewhat dependence on the channel, right. So, what we see over here is the frequency domain view of the signals. So, in case of GFDM we see that the signals are concentrated around one frequency band. In case of the BIDFT N based pre-coding, again we see a similar structure, it is concentrated in one frequency band and hence it is spread in time, right. Whereas, in BIDFT M mode we are seeing that the signal structure is having spreading coefficients across the entire set of signal bands, right. We also have seen some more variants. One is the LFDMA, that means when we do the DFT, we do the DFT over a set of subcarriers which are next to each other, co-located. Okay. Whereas, we can do IFDMA, that means interleaved frequency division multiple access. In that case these frequencies are distributed all over. Okay. They are instead of having localized frequencies, one can have one frequency component here, here, here and there, and the next frequency component would go there, there, there and so on and so forth. So, what we find are some interesting results over here. In case of AWGN channel, when we look at the BER, there is no difference in performance. So, that clearly indicates that these methods does not degrade the performance of a typical GFDM system. So, these are non-degrading pre-coding techniques. Now, when we go to frequency selective fading channel, what we find is that when you are doing this BIDFTM, that means block inverse discrete Fourier transform of size m, that means of the two stage receiver case, you find that we are getting a huge amount of performance benefit, right. The bit error rate is becoming better, and what we also see is that the IFDMA with zero forcing also has some good performance, and so is LFDMA, but in the reverse order. So, this is the best, then this compared to other typical GFDM systems. So, why does it happen? One can understand because there is a frequency domain diversity gain that one gets in this scheme, in this scheme and in this scheme. The more the order of diversity, the more is the gain, and that is what is reflected over here, right, in this particular picture. So, what we gain is that by pre-coding there is no loss in BER in case of GFDM. So, these are non-distortion techniques. However, when we look at frequency selective fading channel, this obviously provides a much better improved performance than other known GFDM techniques. Interestingly, there is also a very important performance metric, which is the peak to average power ratio. So, in peak to average power ratio, what we find is that OFDM, which is here, has a standard peak to average power ratio. A standard form of GFDM has increased peak to average power ratio, whereas if we are doing let us say SVD based GFDM, there is a reduction. If you are doing block DFT-N, there is a similar reduction. Okay. So, this is for SVD based, this is for block DFT based, and if you are doing BIDFT-M, sorry, if you are doing LFDMA, right. So, we get a reduction over here, and if we are doing BIDFT-M, so we see a huge reduction in the peak to average power ratio, and which is also the same as in IFDMA. So, what we find is that this IFDM and BIDFT-M, they provide a similar gain in performance, although BIDFT-M produces a better BER performance than other systems, right. So, what we conclude is that pre-coded GFDM system provides a very low PAPR, which is a very big advantage for providing for low complexity devices, for uplink procedures and all other things, and they also improve the BER performance in a frequency selective fading channel. So, finally, we will conclude this particular lecture over here, and what we will do is, because of time constraint we could not add it in this particular lecture. We will briefly look at the performance comparison of these different waveforms in the next lecture, and then we will move on to newer things, different techniques of 5th generation communication system from the next generation, from the next lecture onwards. Thank you.